Hello, everyone. It seems like it's been a minute since we've talked. Well, a lot of y'all have been asking about this 3.5. I'll show you my notes on it, but I also want to just remind you that every one of these notes is also found in your book under the section. I've modified them, shortened them, and made them a little more useful for us. But you can always go back to your textbook and look at their solutions. They don't just give you a solution, they give you a step-by-step process of how they got the solution. So first thing I want to do before we get into 3.5 is I want to go ahead and find the solution to this compound absolute value inequality. That's a mouthful. First thing I want you to do is remember how do you solve any type of absolute value? Well, we split them up. So the first thing we want to do is let's drop our absolute value bars and make this 2x minus 5y. And then we change both the inequality sign and the sign that's on this constant. So I'm going to change that to greater than and change that to negative 10. If the absolute value bars are in this format here, where they are on the left side of this inequality, then you can remember this ridiculous method. If this is a greater than sign, you use the word or. If it's a less than sign, you use the word and. Then we're going to just rewrite this absolute value inequality without the absolute value bars, 2x minus 5y again, 2x minus 5y, and leave this alone just the way it is, less than 10. Might as well do the same thing for this other absolute value inequality. Let me see if I have any other colors. Yeah, let's try these colors here. I am going to say you can write it as 3y plus 4x. That's just a little bothersome to me. You know what? I can deal with bothersome. I'm going to make that 3y plus 4x, change both of these to greater than or equal to negative 12. This is a less than or equal to, so we are again going to use the word and the second part of this is going to look like 3y plus 4x is less than or equal to a positive 12. All right, I have 4 different colors so I can show you where these 4 lines go. Let's start with this first one. This is, for all intents and purposes, this is standard form. And what I'm going to do is find my x-intercept, then my y-intercept, and then connect those two intercepts together to create my line. This line for this left absolute value inequality is going to be a dotted line since it is not or equal to down there. It's just either a less than or in this case a greater than. So check this out. Cover up the minus 5y. Pretend this says 2x equals negative 10. Divide both sides by 2, you get x equals negative 5. X equals negative 5. On the x-axis, go to the left, 1, 2, 3, 4, 5, and plot a point there. That is your x-intercept. That easy. Cover up the 2x, and you're left with negative 5y equals negative 10. Pretend that's an equal sign just for a sec. And dividing both sides by negative 5, you're like, don't worry about anything else than this. All we're finding is the value of y. What can we multiply the negative 5 by to turn it into a negative 10? We can multiply it by a 2, a positive 2. If y is a positive 2, as in 0, 2, that gives us our y-intercept. As we've already stated, this is going to be a dotted line. Going through those, I don't like that. Up 1, 2, right, 1, 2, 3, 4, 5. Up 1, 2, right, 1, 2, 3, 4, 5. I put as many dots as I can on here just to make sure I get the most accurate line. Goes through that point, and through that point, a dotted line. And that's just stating to the world that anything that falls on this line is not part of our solution. Instead of having a critical point or a critical point or a boundary point, we have a critical line or a boundary line. Now, really quickly, let's throw zeros here and here. We're going to test the point 0, 0 and see whether it gives us a true or false statement. If you put a 0 here and a 0 here, you're going to be left with 0 on the left side. 0 is greater than -10. 0 greater than -10, that's a true statement. So I do want to shade towards 0, 0. I want to shade towards the origin there. So I draw just about 3 arrows here, here, and here to show me I'm going to shade below this line. Let's go green. Now, you're going to find out, well, those of you that are paying attention and do at least 3, 4, or 5 of these types of problems, you're going to find out there's a little pattern here. Over here, our initial x-intercept, our x-intercept was -5. Look at what it becomes over here. When I cover up that -5x, I'm left with 2x equals a +10. So instead of having an x-intercept of -5, I'm going to have an x-intercept of +5. And the same thing happens with our y-intercept. Instead of having a y-intercept of +2, over here I'm going to have a y-intercept of -2. Now check this out. For my red line, I had x-intercept -5, y-intercept 2. For my green line, I have x-intercept +5, y-intercept -2. Whenever you take the opposite of that x-intercept and the opposite of that y-intercept, you can't help it. It's just the nature of the beast. What you're actually going to have is parallel lines. Again, this is going to be a dotted line that passes through all 3 of those points. I bet you it's also going to go towards 0, 0, because if I put a 0 in there and a 0 in there, I'm left with 0 equals 10. That's a true statement, so I want to shade towards the origin or 0, 0 again. Now, before I shade this like sidewalk right here or the street right here or this river right here, notice that there's still a whole second other part to this problem. I can tell you what, I don't consider this hard, difficult, complex, or too much for y'all. It's just extremely tedious. All right, I'm going to pick up the pace, and here's what I'm going to do. I'm going to look for my x-intercept by covering up the y's, and don't confuse them. Like, don't cover this up and think you're looking for the x-intercept because it comes first. Just pay attention to your symbols. It doesn't matter which one you find first. No, not really. I just like to start with my x's. So if this said 4x equals -12, that means x equals -3, x equals -1, 2, 3 right here. That's my first intercept. That's my first x-intercept on the second half. Cover up the 4x. We're left with 3y equals -12. Dividing both sides by 3, I'm left with y equals -4. This time, since I do have a solid line under here, the line that I connect these 2 intercepts with will be solid. Looks like it goes up 1, 2, 3, 4, right? 1, 2, 3, up 1, 2, 3, 4, right? 1, 2, 3. That's just me being extra cautious to make sure I draw these lines as accurate as possible. You'll see when I show you the answer key for the mock exam, the Chapter 3-4 mock exam, you're going to see how we take our time, make sure we go through this. Yes, it's tedious, but it's well worth all the time we put into it. Put a 0 there, put a 0 there. You're left with 0 is greater than or equal to -12. That is true because 0 is greater than any negative number. So again, we're going to be shading towards the origin, 0, 0. Please don't think that's always the case. Every single problem has to be tested because every single problem is unique. And finally, remember what I said. We should already know what our x and y intercepts are going to be. They're going to be the opposite of these 2 right here. The x-intercept is going to be a +3 instead of a -3. 1, 2, 3 to the right. And the y-intercept is going to be a +4 instead of a -4. 1, 2, 3, 4. Down 4, right 3. Down 1, 2, 3, 4, right 1, 2, 3. Do I have room? 1, 2, 3. No, that's good enough. Well, 1, 2, 3, 4. 1, 2, 3. It should go through that point way up there. Solid line that passes through all points that we just plotted. And just for double checked, or for argument's sake, let's put a 0 there, 0 there. I'm sure it's going to go towards 0, 0. Is 0 less than or equal to 12? It is, so I want to shade towards 0, 0. Now these outside arrows here, 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 and here are kind of useless because I want to find out where these two absolute value inequality solutions overlap. So where will they all be true? What shaded region will make this and this true at all times? It's going to be, for lack of a better word, this little diamond or quadrilateral here. This little bit of a parallelogram here. And that is the solution. You're going to have one like this on the test. Again, not hard, just extremely tedious. All right, today's lesson, functions and relations. Keywords. Well, those are the two keywords, a relation. You're going to have to excuse me. I'm going to go off just the top of my head for these definitions. And this is the best I can do for y'all. All my notes are at school. Even my books are at school. So, I don't know. Here's what I see. When we think of a relationship or a relation, it's involving two things. So when we're trying to define a relation, it's just, I would say any two things together, like height and weight, like pay and hours worked. The cool thing about relations is that they don't technically have to be related. They don't have to be related in the sense of like familiarity or family. It doesn't have to be related like the more I study, the better my grades are. It's just anytime you have an ordered pair, I would say that too, maybe any ordered pair. Any X and Y ordered pair. It's just two things together. Now a function, however, a little more specific and a little bit more restrictive on its definition. A function is a special relation where each x value, also known as inputs, has exactly one y value. Or an output. Memorize this sentence, because if you are ever asked in the future in any mathematical class, is this a function? Is the graph a function? Are the ordered pairs a function? Is the table a function? Does any of these representations represent a function? Explain your reason. This is the best explanation here. Okay? You could say, yes, it's a function because each input or each x value has exactly one y value. And that's it, period. Or if it's not a function, you can say, no, it's not a function because each x value does not have exactly one y value. All right, let's talk a little bit more about these functions. All right, let's talk about all the different types of x's that we can have. And usually if we were in class together, we would do a little choral. I would say one word, you would give me its complement back. Like if I said input, y'all would say output. If I said independent, independent variable, y'all would repeat back dependent variable. Let's start with the y value, or a y term right now. Independent variable. If I said this is the effect, y'all would say this was the cause. We can call the x's the if, and the y's are the then. As far as science goes, the if-then statements There's others out there. That's pretty much good enough for me that I can think of. I'll see if I can think of any more, but I thought there was one more that was kind of obvious. Input independent. Cause, effect, if, then. I don't know. I could tell you what, man, since I've been sick with this, whatever I've had, COVID, my brain is a big foggy statement. Let's jump into our first example for the day. State the domain and range of each relation, then decide if the relation is a function or no function. All right. This one's so easy. If they're giving you a set of ordered pairs like 2, 3, -1, 0, 0, -3, and 2, 5, all we're going to do is this. For a domain, we're going to pick all the x values like 2, -1, 0, and 2. We are going to put them in numeric order, and we're only going to write them one time, no matter how many times they appear over here. So out of those four numbers, out of those four x values, the smallest is -1, then 0, then 2. And that's how we write a domain. Similarly, for the range, we're going to go ahead and write the y values. 3, 0, -3, 5 in numeric order. And no matter how many times they appear over here, you only write them once over here. That's the rules for set notation. So I'm going to start with -3, 0, +3, 5. All right. Now, to answer the third question, is this a function or no function? Look at your inputs. Do you see any inputs that are twins? Any x numbers, x values that are exactly the same? I do. I see a 2 there and a 2 there. Do these inputs have the exact same output? Meaning they don't have to be the exact same as that number there, like 2, 2. But here's the deal. Here's what I'm trying to say. I can't remember if y'all were with me. No, y'all weren't. This was another class, another course, another trimester. I'm going to use my filing cabinets when I get to school to kind of show you this, but this is kind of like a Coke machine, okay? It would suck if you went to the Coke machine and you press the second button from the top and it says a Coke's going to come out and a Coke comes out. Well, that's not the sucky part. This is. So then you're like, oh, I got to get one for my best friend, so I'm going to go ahead and put another $1 in the machine. I press the second button, but this time, I don't know, think of your worst or least favorite drink. Maybe, I don't know, maybe seltzer water comes out. You wanted a Coke, you were dying for a Coke, thirsty for a Coke, and out came something else. So you can notice right now, this input has a 3, while this input has a 5. It breaks this rule up here. Each input does not have exactly one output. This one has 2 outputs. It's unpredictable. It's unreliable. So this is no function. All right. This time, for example 1b, we're just going to look at this graph. And what I'd like to do, let me see, what do I have thin enough over here? I don't know, maybe this wire. You use your pencil usually, or your straight edge or ruler, and what you do is something called the vertical line test. You're going to drag this vertical line across the graph, and you're going to see if it ever touches more than one spot simultaneously. How many times does it touch there? Once, 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 once. It will never ever touch the graph, this vertical line here, or this vertical line here, or this vertical line here, your pencil. It never touches the graph more than once in the same vertical line. If you drew vertical lines here, it only touched once there. Another vertical line, it only touched once there. Another vertical line, if you notice every one of those vertical lines only touches our graph once, well, that is a way of saying each x value has exactly one y value. Each input has exactly one output. So here's our domain. This is pretty cool. I'm going to read it like a book. I want to see what's happening to the left and to the right. This is going forever left. Even though that looks like that X arrow is going up, it's going up and left. I should draw it more like that. And this is going up and right. So if it goes forever to the left, forever to the right, it includes all the negative x's, all the positive x's, and even 0. We're going to say x is equal to The domain is x equals all real numbers. You can even get away with just saying all real numbers, and I got you. You don't have to say x equals in this situation. Now, let's take a look at our domain. This time, we're looking at the y movement, the up-down movement of our graph. Obviously, we have agreed that it goes forever up, but does it go forever down? No, it does not. It starts down here at 0. So we're going to say y is greater than or equal to 0. But remember that good old interval notation where we say what's the smallest y value, what's the greatest y value, and using using brackets or parentheses, we say this. Y will go from 0 to infinity. It starts at 0 and it goes forever up. There's no negative values for y. So that's how we write our range. All right, we looked at ordered pairs, we looked at a graph, and now we're going to actually look at an equation. Here's what we're going to do with this equation. Circle this. At this point in college algebra, we only exist in the real number, real world realm. We don't want imaginary numbers. So we can only take the square roots of non-negative numbers. So what we can do is take everything underneath the radical, the x minus 25, and make sure you set it greater than or equal to 0. Now solve for x. Add 25 to both sides. X has to be greater than or equal to 25. The smallest number x can be is 25. If you put a 25 in here, you'll get 25 minus 25 is 0. Yeah, you can still take the square root of 0 at 0. But you don't want this x value to be any smaller than that 25. The smallest it can be is 25. So how do we write that? We say bracket, it goes from 25 to infinity. Now let's think about the y values. If the smallest number you'll ever have under here is 0, not the smallest x, the smallest quantity under here, it'll never be less than 0. What's the square root of 0? It still equals 0. What number times itself equals 0? It's 0. That means y will never be negative, so y will always be greater than or equal to 0. So you write it just like we wrote it over here. Bracket 0 to infinity. Now let's talk about whether these were functions or not. Over here, we talked about that vertical line test. It passed the vertical line test, so we say it is a function. Over here, what you got going on is something that looks like this. Sketch a quick graph for you. When x is equal to 25, y is equal to 0. So that's our x-intercept. And then, I wish I could explain this to you. I kind of remember it this way, goofiest way. You know this thing called a radical right here? Well, I'm going to kind of, I don't know what to call it. I'm going to reshape it just a little bit. In fact, I just want to focus on this little part right here. I know this isn't exactly the best way to teach it, but sorry, this is the way I'm doing it. That's what the graph looks like. It's going to go up, and it's going to keep going up and right forever. It's kind of like an airplane taking off and then coming to a cruising altitude. It just never, ever, ever gets flat, and it'll never come down and land. Now, looking at this guy right quickly, it also passes the vertical line test. Clearly, it never, ever touches. No vertical line will ever touch this graph more than one time anytime it stops. Right here it touches once. Every one of those vertical lines touches this graph once and only once. So in other words, each input has exactly one output. So this is a function. Now the one on the example I'm going to give you on the test, I'll tell you right now, it's not going to be this hard or this difficult. One of these is going to be the equation of a line. I think this one, instead of showing you a graph, I think I do an equation of a line. And I can tell you right now, this is the domain and range for every non-vertical and non-horizontal line. It's going to be x equals all real numbers, y equals all numbers. I'm sorry, x equals all real numbers, y equals all real numbers, and every single line. except for a vertical line. Every single line that exists in the world is a function. So anyway, pause if you need a break. I'm going to keep pushing forward. Example 2. State the domain and range of each relation and decide if the relation is a function or no function. This is almost identical. I think my intent for this problem was for me to give you all a chance to do it by yourself. So go ahead and pause it right now and then check your answers with mine. Welcome back if you actually paused it. I'm looking at my x values. I have 3, -3, 7, -1, and 0. Let me put them in numeric order. -3, -1, 0, 3, 7. Put them in braces because we write them in set notation. For your range, let's go to the second set of values, the 7, -7, -2, 7, -1. And in numeric order, that's going to be -7, -2, -1, and 7. There are 2 7s in the y spots, but I'm only going to write it once. That's how we write sets. Function or no function? Well, I call this the twin test. Only thing you have to focus on right now is the x values. 3, -3, 7, -1, and 0. I don't see any twins there. I see opposites, but I don't see any identical twins. If there were identical twins, we would have to do a further second investigation. If there were identical twins, like there was in example 1, we're going to have to see if the 2 identical twins have the exact same outputs as each other. And if they do, right on, it's a function. If they don't, it's no function. Here, if there are no identical twins, you can always assume it's a function, because the only time we say no function is if we can prove it's not a function. We can't prove it's not a function right now. All right? When you're given a graph, we're going to use the vertical line test to say whether it's a function or no function. But check this out. Remember, this is our x-axis. I know I didn't do that on the last one. Anyone, y'all trying to get your stickers caught me. I don't know. I'll pretend that's a 2 and maybe that's a 4 up there. The way it kind of looks, that's kind of what it's looking like to me. Because it doesn't really matter what those numbers are. Don't wrap or get too confused. Like, I don't know how you got that number. Chill, man. It's all right. I just need you to know this. What's happening? Am I going forever left and forever right? Well, I am going forever right, but I'm not going forever left. I'm actually starting at 0. So I'm going to start at 0, including 0, and I'm going to go to infinity. That's my domain. 0 to infinity, including 0. Now look at my range, the up-down movement. It goes forever up and forever down. How do I know it's going forever up? Well, after a while, you know what? That light's bothering me. Sorry that I didn't notice it till now. Try this. Yeah, that took all the shadows away from me here. I'm just kind of working in the dark now, a little darker. That's all right. What's happening here is this. This is moving right and up, right and up, right and up. It's not moving at a constant rate. To me, it looks like it's going up. It's going up faster than it's going right. Its vertical shift or vertical movement is greater than its horizontal movement. But regardless, every time it moves up, it will also move to the right. Now, what am I thinking about right now? Oh, the whole reason I'm telling you that is because you need to, in your mind, understand what this end behavior is going to look like. I know I'm kind of messing with this arrowhead and this one too, because it's actually moving in 2 directions. I don't want you to think it's just moving to the right here. I don't ever want you to think that this will get horizontal. It might look like that, but remember this. Thank goodness for many of us, thank goodness for many of y'all, looks don't matter. Oh yeah, that was a joke I used to say in class. Looks don't matter. Yeah, for sure, looks don't matter. And what I mean by looks don't matter here is don't say, oh yeah, that's going to the right. No, it's not going to the right. It's not just going to the right. It's going right and down. This is going right and up. Keywords, it's going up forever. It's going down forever. So the y values are all real numbers. All the positive y values. We're just trying to say what y values work here. Remember, for domain and range, what's the definition of domain? The set of all x values that work in a function. What is the range? The set of all y values that work in a function. So this includes 0.01, 0.02, 0.03, 0.04. It includes smaller numbers than that. It also includes the numbers 0.1, 0.2, 0.3, 1, 2, 3, 4, 5, 6. It includes every single positive number, decimal fraction, don't matter, whole number. It includes every single y value that's a negative number, and it includes y being at 0. So it's all real numbers. Now, here's a clear case. If I try the vertical line test, I drag it across. The only time this vertical line touches my graph once and only once is right there at that vertex. Anywhere to the right of that vertex, look right here. If I drew a vertical line, it touched twice. And what that means is when x is this value, I actually have two different y values. Well, we can't have that and have it be a function. So this is definitely no function. It failed the VLT, or the vertical line test. Hey, here's my favorite of all. What is this? Y equals 3x plus 7. This is the equation of a line. And as long as it has any slope to it, this has positive slope with a positive y-intercept. I don't care what it looks like. It just looks something like that. It has positive slope and a positive y-intercept. Quick sketch. Here is the easiest answer ever. X equals all real numbers, y equals all real numbers, and 99.9999999% of lines are functions. The only line that is not a function is a straight up vertical line. So there you go. Let's try example 3. State the domain and range of the relation, decide function or no function. All right, this ain't hard, guys. This is in the book, and this is what they're going to want you to do. Let's figure out any restrictions to our domain or to our range. So first of all, here's the deal. I hope this is ingrained in your head, and just because I have not been there doesn't mean you should not remember this. What is the only number we can never, ever, 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 ever divide by? That number is 0. So let's make sure that 2x minus 10, my denominator, my downstairs quantity, is never equal to 0. Instead of setting it equal to 0, set it not equal to 0, and then still solve for x the way you usually would. Add 10 to both sides. 2x can never equal 10. X can never equal 5. If you put a 5 in there, 2 times 5 is 10, 10 minus 10 is 0, you have issues. Issues that I can't help. So here's what we can say. We can say that x equals all real numbers. Don't like x to be red. I like for it to be blue. X can equal all real numbers, except for x cannot equal 5. Okay. This bottom quantity can never be 0. It can be positive. It can be negative, but it can never be 0. You can divide by positive numbers, you can divide by negative numbers, you just cannot divide by 0. So if the bottom can never be 0, and if the top has a solid number 3 over there, 3 divided by negative numbers is negative. 3 divided by positive numbers is positive. So y will always be positive or negative, but y itself will never be 0. So for your range, you can say y equals all real numbers, except y will never equal 0. There's no way to turn this side into 0, because it's always going to be a positive 3 divided by a negative number, or a positive 3 divided by a positive number. So y is always going to be either a positive or negative number, but it'll never, ever, ever be 0. Now, This is known as a rational equation or a rational function. And this, I think what I've done on the test, just heads up, I think I took this part out of the test where you have to decide function or no function. I really don't want you to worry about it too much, like, oh, I don't get it. I'm going to be holding a Zoom session sometime this week, probably Tuesday, January 11th. I'll be having a couple different Zooms just in case you can't make the first one or the second one. You can make at least one of them, and then I'll be able to answer some questions. You don't have to come to it, but if you want to come to some tutoring, that's going to be my tutoring hours on Zoom since I can't see y'all in person. I do want you to be able to decide function or a function, especially for these easy ones like a line or a set of numbers like this, or even a graph. And unless it's a special case like this, or a special case like one of these down here, I just want you to understand, probably when in doubt, say it's a function, okay? That's my best advice for you there. Look at example 4. State the domain and range of the relation, decide function and no function. All right, this is the equation of a circle. I can't remember how many of you all worked with circles with your last teachers, but basically here's what's happening. Let me explain it to you real quick. I drew this here, or I put this here so we can do a sketch of this. The equation of a circle looks something like this. It's going to be something like x squared plus y squared equals r squared, r being the size of our radius. And if this has the exact same coefficient that this does, preferably 1, 1x squared plus 1y squared, that is the equation of the most perfect shape I can think of on here, a circle. Now, if one of these has a different coefficient, then it's going to be elongated, kind of like an egg or an ellipse. So I don't need you to get into all that. Maybe we'll talk about it later. I'll see if I can squeeze into later lessons, but I want to do this. If this r squared equals 9, that means our radius is going to be 3. I'm not adding anything to this x squared. Like I don't have x plus 7 quantity squared. I don't have y minus 5 quantity squared. So that's nice, because if you don't have x plus something quantity squared, and if you don't have y minus something quantity squared, it's just a straight up x squared and a y squared, then that means the center of your circle is at 0, 0. So my center's here, and it's going to go up 3, down 3, right 3, left 3. And there's my shape. So that helps me talk about my domain and range. Here's my domain, the x-axis. It goes from -3 to +3, including both of them. So I use brackets, -3 to +3. Same with my range. It starts down here at -3 and goes up to +3. And this fails the vertical line test. Drag a vertical line across it. If you need to, sketch that vertical line. It touches twice. Anytime it touches more than once in one spot, it is not a function. All right. Example 5. State the domain and range of the relation, decide function or no function. All right, let's get rid of these parentheses by distributing. Y equals 3x minus 3 plus 2x plus 2, or y equals 3x plus 2x is 5x, minus 3 plus 2 is minus 1. This is a beautiful line. What do we know about lines? Especially if I didn't say vertical lines, just regular old lines. Easy. X equals all real numbers. That's its domain. Y equals all real numbers. It goes forever left, forever right. It goes forever up, forever down. And every non-vertical line is a function. What's your function? Example 6, real quick. We have graphs, we have equations, and we have more equations. All right, it's as simple as this. Vertical line test. Drag a vertical line across this. Once. This is definitely a function. Its domain, it goes forever left, forever right, so x equals all real numbers. It also goes forever up and forever down, so for the range, y equals all real numbers. This one's a bit harder. There would be no way I'd give this to you unless I told you what that number is there. I'm going to pretend that number is -5 right down here. As I drag this vertical line across my graph once, every time I stop, I don't like those jerky stops. I'm going to go smoothly across, and I'm just going to say once, once, all the way across. A little Cardi B. So I know this is a function. If you ask me why, I could say because every input has exactly one output. Here we go. Domain. I'm talking about left and right movement. It goes forever left. Even though it goes down, it's going left, 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 right, 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 right. All the negatives, all the positives, including 0. So x equals all real numbers. For my range, it starts down wherever that value is there, -5. It goes up to 0, then back down to -5, but then goes up to infinity. And over here it goes up to infinity. So it looks like the lowest it'll ever be is -5. So we'll say y goes from -5 to infinity, including -5. Use a bracket. We have another rational here. We want to make sure we take the denominator and set it not equal to 0. So that means x cannot be -5. For my domain, x is all real numbers except for -5. A -5 would create a 0 in the denominator, and we can never, ever divide by 0. For the range, it's going to be exactly like the range we talked about up there. Y will never be equal to 0 because this will either be a positive or a negative, but it'll never be 0. And again, 3 divided by positive is positive, 3 divided by negative is negative. There's no way to turn this into a number 0, so the y values for our range are all real numbers, and y will never be 0. This is a rational function, so we say yes, it is a function. And I saved the best for last. This is a line in point-slope form. My point that it passes through is the opposite of that, So it passes through the point -3, +2, FYI, and it has a slope of -4/7, down 4, right 7. Keyword, line. Domain, range, x equals all real numbers, y equals all real numbers. Every non-vertical line is a function. What's your function? That's about it. Thank y'all. Have a good day. Let me know if you have questions. Sorry you couldn't see that. Let me squeeze it over here. I hope that was the only one you cannot see. Give you about 10 seconds to check it out one more time. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Pause, freeze. All right, guys. I'm done. I'm sorry. I'm tired. I got to go get your... I got to get this posted and then put the